This conference will now be recorded.
Everyone. So in this video, we will discuss problems from the chapters, that is previous year's problems of JEE Main from the chapter Basic Principles of Organic Chemistry. Here we have the first question. Among the following compounds, the one which shows highest dipole moment. So we have to find highest dipole moment that will be found in which compound. Now in this case, we have some double bonds that you can see. So compound 1, we have CC double bond, then we have C double bond O, then CC double bond for compound 3 and 4. So in this case, what will happen? There will be some charge separation. Charge separation means suppose we have CC double bond and there is any other substituents. Now if I am breaking the pi bond, there will be positive charge over one carbon and negative charge over another carbon. Okay. Similarly, if we have C double bond O, as oxygen is more electronegative, so that is why positive charge will be over carbon and oxygen will be negative. Now, if we are doing so, that is charge separation, then there is some polarity generated. That means where the maximum amount of charge separation will take place, that is the molecule where highest dipole moment will be found. Now, why this charge separation will take place? That is the question. The reason behind this charge separation is after charge separation, there will be some aromaticity factor generated. And aromaticity when generated, that is the driving force for stability. And that will increase stability of this molecule. And that is the driving force why this type of charge separation is occurring. Now, if we consider the first molecule, here after charge separation, positive charge will be in the left hand side, and in the right hand side molecule, which is 5 member, there will be negative charge. Now why I have drawn so? Why I am not doing the reverse? That is, why not negative charge in the 3 member ring and positive charge in the 5 member ring? Now there is a reason behind it. If I am doing this type of separation, that is positive charge in the 3 member ring, then the species that we are getting both sides, both are actually aromatic. And that is the reason why this type of charge separation will be there. Now the conditions for aromaticity that we know, though still I am just writing it here in short. So the first condition, it must be planar. The second thing is this, there should be conjugation, full conjugation, not just simple conjugation, full conjugation over the ring. It must be cyclic. As it is cyclic, so the conjugation that will also be through the entire ring structure. And the 4 is 4n plus 2 pi electron rule that must be satisfied. So in this case, you can see we have total 2 pi electrons because we have only one CC double bond, and that is actually satisfying 4n plus 2 when n value is 0. And then it is cyclic, there is conjugation possible, and it is planar. And thus all the 4 conditions are also fulfilled if you consider the second part of this molecule. Here we have total 2 double bonds and 1 negative charge, that means total 6 pi electron. Now 6 pi electron is possible when n value is 1. So 4n plus 2, n value 1, that means total 6 pi electron. And then this part is also planar, cyclic. Throughout the entire ring there is conjugation. So that is why this type of charge separation will be there, because it is leading to generation of 2 aromatic species both sides. So here charge separation will be maximum and we can expect very high dipole moment. But we will also check the other molecules. In the second molecule, if I am doing charge separation, it will be something like this. Now there is no question of aromaticity generation. It is not bringing any extra stability. Then compound 3, here both side we have 5 member ring. So whether you put plus charge over this carbon or the other carbon, it doesn't matter anything. Now if I am putting plus charge over one and negative over other, one thing we have to notice, this side is aromatic, it is fine. This side is aromatic, it is okay. But this side is basically anti-aromatic, because the anti-aromatic conditions are that all the first 3 conditions will be same as aromaticity conditions. But the last one, instead of 4n plus 2, now we will have only 4n. And look at this left hand side species, we have 2 double bonds, that means total 4 pi electron present here. And as 4 pi electron present, it is basically satisfying the conditions for anti-aromaticity. So in molecule 3, if you are doing charge separation like this, basically you are getting one aromatic species and one anti-aromatic. So still we can say that compound 1, where we are getting 2 aromatic species, obviously it will lead to more stability. Then what about compound 4? Now both sides we have similar size ring, and even if we do some charge separation here after removing this double bond, but remember here we have 2 sp3 carbon, so full conjugation throughout the ring is not possible. Even if it is satisfying aromatics, that is 4n plus 2, then also it will not work, because throughout the entire ring conjugation is not possible. So maximum charge separation we can see in case of molecule 1, and that is why it will lead to the maximum dipole moment, because this molecule basically will remain in this condition, that is positive charge over the left hand side ring and negative charge over the right hand side. So this will be the correct option. Next question, the decreasing order of hydride affinity for the following carbocations. Now what is hydride? Hydride is basically negative charge over hydrogen, that is called hydride. Now hydride affinity means the positive charge that is present in carbocation, it is obviously searching for some negative charge. So that is why obviously it will have some hydride affinity. But remember, if the carbocation itself is very stable, it will not try to find any hydride, because it is already stable. Why it will try to find some hydride? So it means when stability of carbocation is very high, hydride affinity becomes lower. So this question is basically asking the stability order of carbocation. But once you find the stability order of carbocation, you have to reverse it, because the relationship of stability of carbocation and affinity towards hydride, these two are reverse to each other, right? So here if you look at the options, it is written with comma, C comma A comma like this, but it is actually, we have to find decreasing order. That means all these are, if I'm just putting this type of sign so that it will be easier for you to understand. So ACBD, it is, they are written with comma. It means what? Here it is already mentioned decreasing order. That means A will show maximum hydride affinity and D will show minimum hydride affinity. But suppose option 1 is correct. So in this case, D is basically maximum stable carbocation, because these two are reverse. So let's find first what is the stability of carbocation order. Here the first molecule, positive charge over carbon. Here we have total 2 methyl groups, that means hyperconjugable hydrogen, total 6. And this side we have CC double bond, and because of this type of resonance, here we are getting some stability. But we also have to check the other 3 species. In case of molecule B, that is carbocation B, here we have total 3 pH. Now 1 pH if I am writing in this way, that is full benzene ring. Now this positive charge, resonance is possible with the double bonds of benzene ring like this. And as a result, what will happen? There will be very high amount of resonance. And all because of all these reasons, ultimately it will lead to very high stability. Then in C, here we do not have any double bonds, but total 3 methyl groups are there, and total 3 methyl groups, that means total 9 hyperconjugable hydrogens. Okay. Now, if we compare B and C, in both cases there is some stability factors are operating, but we have to give more preference to the phenyl ring because extended amount of conjugation possible. Here it is true that total 9 alpha hydrogen, that is hyperconjugable hydrogens are present, but the factor that 3 pH groups are present, it will overcome it. So B will be more stable than C. Now what about D? Now at a first glance it seems that 3 cyclopropane rings are attached. Here we have only 1 alpha hydrogen as if in these positions, and there is no CC double bond, no conjugation is possible. But actually what happens when there is cyclopropane ring attached to carbocation, there is some special type of stability present, and that stability is basically because of this. Suppose this CC bond is there and there is some sigma bond. So this sigma bond electron density, it basically what does, it stabilizes this positive charge, and as a result this CC bond is broken, and as if it is making a double bond here. Now positive charge is here, so as if this bond is broken and we are getting a CC double bond. And this type of resonance, that is known as a dance, sometimes it is called as dancing resonance. But remember, this type of presence of cyclopropane ring, here this CC bond, their positions are in such a way. Now don't expect it with some other groups, don't expect it from CH3 or any other alkyl group. It is possible only when there is some cyclopropane ring, because now the CC sigma bond, its position or orientation compared to the vacant p orbital that is present in this carbocation, the position with this sigma bond is such that it can stabilize this positive charge by giving some electron density, and that is why here stability is possible. So because of this special kind of stability, if we write now the stability order, stability of carbocation order, maximum stable is basically D, and after D the next stability we can expect from B, where you have total 3 pH groups. After B the next stability it will be for C, and at last position sorry it is not B, it is A. Why it is A? Because see, in C and A if you compare two methyl groups present in both cases, that is common, but here we have one CH3, here we have CC double bond, and obviously resonance factor you have to give more preference. So that is the reason this will be the stability order of carbocation. Now if this is the stability order of carbocation, the hydride affinity order, that should be reverse like this, and that is why option 2 should be the correct option. Okay, using column chromatography we have that is mixture of two compounds, we have A and B, and it is observed that A eluted first, and obviously that means B is eluting next after A. Now what it means actually, we have four options, low RF for B, because all these informations mentioned in options they are for the compound B, right? So either low RF and either weak absorption or strong absorption, and low RF with weaker, low RF with stronger, like this. All we have total four options. Now when we have two mixtures in column chromatography, though it is column chromatography, now the picture it is shown like that, don't think it is paper chromatography. It is, the theory is actually same, so that is why you can also observe it for this type of strip. If we draw the picture, there is no issue. You can also do it in column chromatography because it is already mentioned. So when you are doing it for column chromatography, what will happen, A will be eluting fast. Here you can see A is moving fast, but if you consider column, because it is now anti-gravity, right? Sorry, towards gravity, it is anti-gravity. That a picture if you consider in strip, it is anti-gravity. So here it is A and it is B, and in this case what will happen, A will come first and after that B will come, right? Now when it is so, obviously it will be stronger absorption for B because it is strongly absorbed, and that is why it is coming after A, right? So that is why either option 2 or 4 we have to choose. Now whether it is high RF or low RF. Now what is RF? What is the meaning of RF? That we have to know. So here you can see RF is basically the distance moved by the analyte divided by distance moved by the solvent. So the solvent, that is the, for elution purpose, the solvent that we use, there will be some distance covered by this solvent. So this is the distance covered by this solvent, and then we have distance covered by the analyte. So here we have some qualitative picture, though it is not mentioned that what is the distance, we have just here, just can have some qualitative idea. So this is the solvent distance and it is the distance for analyte A. suppose it is somewhere here, and for analyte B it is somewhere here. So obviously this distance, when you consider compared to this 4 centimeter distance, obviously it will give you higher RF. And when it is analyte B, now it is only this amount of distance compared to this amount. So obviously this ratio, now it will be low. You can also consider it for column. So the distance traveled by analyte, obviously that will be higher compared to these two, because when you are first putting the solvent will take this A and B one by one depending on which one is more polar. So here A is less strongly absorbed, that means it is less polar, so it is coming first. So that is why it will be having higher RF and B will be having lower RF. So here we have taken just some values to make you understand. So it will have low RF and stronger absorption. That means option 4 should be the correct option. Match item of column 1 and column 2. So in column 1 we have some mixture of compounds, and in column 2 we have some name of separation technique. So we have to find which one is matching with what. First mixture we have water and CH2Cl2, water and dichloromethane. Now these two mixture both are basically liquid, and DCM is basically organic solvent and water, aqueous part. Now this is very ideal if you separate it by solvent extraction. So in solvent extraction, what we take a separating funnel like this, and there is a stopcock here. Now when you put the mixture of water and DCM, water part will be at the higher level and DCM will be at the lower level because it is heavier compared to water. So, and you can easily that is a layer between these two, easily visible. So when you open the stopcock, you can separate this part, which is basically DCM. So this should match with differential solvent extraction. Then in option B we have, okay, if A is 2, it is matching with this one, option 1 and option 2. Next we have compound, that is mixture B. Now here both are actually solid. Now when both are actually solid, and there must be some polarity difference. If you look at this molecule carefully, this OH group and NO2 group is there. Now this type of resonance is possible, and as a result there will be some charge separation. You can also consider hydrogen bonding between two para-nitrophenol. Now because of this type of charge separation, that is resonance, because OH is having plus R effect, NO2 is having minus R effect. So plus minus charge generation is possible, plus charge over oxygen, and there will be negative charge over NO2 oxygen. Now as there is polarity difference, and we can use column chromatography for this molecule. So why, if you are thinking why not to do crystallization, but see there is another mixture which is glucose and sodium chloride. Now this is very ideal for crystallization. Okay, why? Because when you will try to crystallize with ethanol, in ethanol NaCl will not be soluble, but glucose will be soluble because its carbon content, total 6 carbons are there, so it will have solubility in ethanol, and you can easily, that is NaCl will not be dissolved, so you can separate it out by filtration. And the ethanol part where glucose is present, if you that is evaporate some amount of C2, some amount of ethanol, which is the solvent you are using for crystallization, gradually you can find the crystals. Okay, so this method is good for it. And there is kerosene and naphthalene. So kerosene is naphthalene, both are liquid, and as there is, that is boiling point difference is not very high. So for liquid separation, distillation is very good, but here fractional distillation is maintained, written, and that is the distillation we actually have to apply because the boiling points are close. So C should be matching with 4. Okay, so C is matching with 4, D is matching with 1. So that means, and V is 3. Column chromatography we will use, where this compound will come eluted first, and then the para-nitrophenol. Okay. Correct order of aqueous medium basic strength in case of methyl substituted amine. If you look at the options, here we have total 4 types of amines. One is NH3. Now gradually, as if we are attaching some methyl groups, MENH2. Next one is Me2NH. And the third one is all the hydrogens are replaced by Me group. So total 4 species we have. Now it is asking aqueous medium basic strength. Now this aqueous medium basic strength is very important, because if it is asking gaseous medium basic strength, then the answer, and the answer if it is asking aqueous medium basic strength, obviously these two answers are not same. So read very carefully whether it is asking aqueous medium basic strength or gaseous medium. Now why it is so? Now, when it is gaseous medium, there is actually one factor that is operating, which is plus I effect. As the methyl groups are increasing, you are moving from ammonia to methylamine to dimethylamine to trimethylamine. Basically, number of methyl groups are increasing. That means plus I effect is increasing, right? Now, plus I effect increasing means what? Extra amount of electron donation effect. That means lone pair availability over nitrogen, because of this plus I effect, that will over nitrogen, that will increase. Higher is the number of methyl, higher is the basicity, because lone pair density is high. Now this type of explanation is applicable only when you are considering plus I effect, and that is possible in gaseous medium. But when it is aqueous medium, you also have to consider another factor. So based on plus I effect, the order should be like this: Me3 and maximum basic, after that Me2NH, after that MENH2, and at last ammonia. But when it is aqueous medium, there is another factor that you have to consider, and this another factor is the conjugate acid solvation factor you have to consider. Now from ammonia, the conjugate acid that you will get, it is basically total 4 hydrogen attached to ammonia, positive charges over nitrogen. Now the conjugate acid that you get from MENH2, it will be like this: 1 extra hydrogen and nitrogen is positively charged. Similarly, from Me to NH2, the conjugate base that you will get, it will be like this. Now one thing is you can understand here, gradually the number of hydrogens are decreased. Now as it is solvation effect and it is aqueous medium, so there is some hydrogen bonding possible with water molecule, which will stabilize this conjugate acid. Now higher is the number of hydrogen attached to this nitrogen, positively charged nitrogen, higher will be the solvation. Here only 3 OH2 can be attached. Here only 2 OH2, and in case of this only one water molecule. So solvation effect if we consider, then maximum stable is this, then this. So it is completely reverse compared to the previous. Now what will happen in aqueous medium? You have to take the combined effect of these two reverse effect, because according to plus I you are getting this result, according to conjugate acid solvation you are getting another type of order. So what you will do? You will take the combined effect, and when you take the combined effect, actually what happens? Now Me to NH will show maximum basicity. After that it will be MENH2, that is 1 methyl substituted ammonia, then Me3N, and this is ammonia. So remember here, plus I effect and the conjugate acid solvation effect, both effects are operating, and you have to take the combined effect, which will give you this result. Match list 1 with list 2. So in list 1 we have some compounds given, and in list 2 there is some specific name for this type of compounds are mentioned. The first one, here we have 5-member ring with 1 oxygen. And look at the list 2: spido compound, aromatic compound, non-metal, non-planar, heterocyclic, and bicyclic. Now this is obviously not bicyclo. This is also not spido, because spido is something where just you can draw it like this, where one carbon that will be attached to total 4 other carbon, and there will be 2 cyclic structure. Now it may be 3-member ring like this, or it may be 3-member ring with a 4-member ring. But this type of structure where one carbon as if the connection point of two rings, that is actually spiro compound, and that you can find in option C. So C should be matching with 1. Now if you are considering C matching with 1, you can easily consider option 3 as the correct option, because C is matching with 1, that you can get only in option 3, right? Now here we also have bicyclo compound. Now A and D are not bicyclo, right? So bicyclo compound is option B. So B is matching with 4. So option 3 is, we are also seeing that. Now what is the difference between A and D? In D we have these two CC double bond. And because of this CC double bond, all these carbons are basically sp2. That means here the structure will be planar. But here all these carbons are sp3, tetrahedral carbon. That means it cannot attain planarity. But it is true that it is heterocyclic compound, right? Because we have one oxygen. So non-planar heterocyclic, A is basically matching with 3. Though it is also true A matching with 3, that you can get only in option 3. So based on compound 3 alone, based on compound A alone or C alone, you can also choose answer if you are lacking in time or you are in hurry. Fine. And B is matching, 2 is matching with D. Now, why the last compound is aromatic? This compound is aromatic. The reason is here this lone pair is basically also the part of aromaticity. This type of conjugation is possible. And as a result, there is total 6 pi electron which is matching with 4n plus 2 rule. And here n is 1, that is what is matching with 6 pi. And the other factors for maintaining aromaticity, that is it must be planar, cyclic, and the full ring conjugation. Everything is present here. That means it is aromatic compound, and that is why D is matching with 2. So option 3 is the correct option. Among the following marked proton, which compound shows lowest pK? So here you can see these are the marked protons. And lowest pK means what? Maximum acidity. pK and acidity, these two are inversely related to each other. So we have to find that compound where maximum acidity is possible. Now suppose I am considering a general expression for acid which is Ha. When Ha is dissociated, you are getting one proton and you are getting A negative, which is basically conjugate base of Ha. Now if the stability of this conjugate base is very high, stability of conjugate base when high, that means acidity of Ha is also high. Because stability high means what? The equilibrium can be easily shifted towards right hand side because it is generating some stable species. That means this type of dissociation to H plus and A minus, when it is very high, obviously the acidity of Ha is high because you are getting more number of protons. Now we have to check in which case after removal of H, the negative charge over carbon that you are getting, that negative charge is stable. Because if the negative charge is stable, that means the corresponding conjugate base is stable. So from the first one, we are getting H2C negative, then we have CO2H group. From molecule B, we are getting COCH3, right? Now, for the option C, here we are getting negative charge, COCH3, and from the last one, we are getting negative charge, COOH. Now, we will check in each case what type of resonance is possible. Here, if I am writing it COOH like this type of resonance possible. But remember, this C double bond O, that can also take part in resonance with the OH group. This type of resonance is also possible. That means this C double bond O, it cannot take part in full, that is full resonance with this CH2 minus left hand side is not so easy because it is also taking part in resonance with the OH group in the right hand side. Now what about the next one? In the next case, here this type of resonance possible. So it is in this case C double bond O, that is the double bond character of carbonyl group is high compared to the previous one. What about the option C molecule? Option C molecule, here this negative charge in the COCH3 site, there is some resonance possible. But remember, we also have pH ring. So in the left hand side also, there is some resonance possible with the benzene rings double bond. So both sides we are getting some stability. And in case of last one, here also we have pH just like option C, but this side we have COOH. But remember, compared to COCH3 group, if you consider COOH, the case is just like these two, where we have seen in COOH another, that is resonance with OH group is also possible. As a result, the double bond character of CO group is decreased. That is the reason that CO2H group is that is COCH3 group is better in stabilizing negative charge compared to CO2H. So considering all the factors, we can choose option C as the correct option. It is the molecule where the negative charge at this position, it will be maximum stable, and that is the reason it will show lowest pK. That means it is highest acidic. Which technique among the following is most appropriate in separation of mixture of 100 mg of para-nitrophenol and picric acid? So para-nitrophenol is this one and picric acid is, here we have some extra NO2 group at 2 and 6 position also. Sorry, NO2. Now, if you compare these two molecules, there will be some polarity difference because in the second case you have more NO2 groups. So this lone pair over oxygen, when it will take part in the resonance even with the NO2 group, that will be more in case of second one. So there will be some polarity difference because when we are trying to separating it, suppose if you are doing chromatography, obviously polarity difference must be present. Now both these are basically solid molecule. So steam distillation is not possible. It is better for low boiling solid or sorry, not low boiling solid. I'm saying that is which can easily melt, and most of the time is easily melt. That means it can easily reach the liquid state, but that is not possible here. So steam distillation will not be correct. Next we have 2 to 5 feet long, but see, this is only 100 milligram mixture. This is very less quantity, and 2 to 5 feet long is very, that is the size is so large. This type of column you can use when you have very large amount compound. Okay, not this scale is suitable for it. Then we have sublimation, but sublimation you cannot do not for any just any molecule. There must be some sublimation property, otherwise you cannot do it. So in this case it is not possible. So only option left is preparative TLC, thin layer chromatography, because here column chromatography, even if you do not do it, doesn't matter because the amount is very low and this amount is suitable for preparative TLC. Okay, so we can choose this method. This is the appropriate method. Arrange the following in increasing order of reactivity towards nitration. Now we will try to see what is nitration reaction, and all the 5 species that you are seeing, all are basically benzene based. So if I draw benzene, and nitration means we will use some mixture of HNO3 and H2SO4. Now why we use this mixture? Because this mixture will generate the species NO2 plus, and this is actually our electrophile. Now this is the electrophile which will be attacked by the double bonds of benzene ring. That means here benzene ring is acting as nucleophile and NO2 is acting as E plus. That means if you can somehow increase the electron density in the benzene ring, that is if there is some donating groups, obviously now the attacking tendency towards E plus for the benzene ring, it will be high. Now we will draw all the structures. Compound A is xylene. Paraxylene is this molecule where we have 2 methyl groups at ortho para position. If I am saying orthoxylene, it will be 1 and 2 position. Then we have compound B, bromobenzene. Then we have mesitylene. Mesitylene is total 3 CH3 groups present at 1, 3 and 5 positions. Then compound D, nitrobenzene, we have 1 nitro substituent and then we have simply benzene. Okay. Now, if we check in which case there is maximum amount of electron density is increased, methyl group is donating group, and here we have total 3 methyl groups. So it should show maximum, it should increase the nucleophilicity of benzene ring towards NO2 plus electrophile, right? And this should be minimum, because NO2 group, it will show minus R effect as well as minus I effect, both. So it will decrease the electron density, it will decrease the nucleophilicity of benzene ring. So this should be at the minimum. So D minimum, C maximum. That means option B should be correct. This is at the maximum, this is minimum. So even if you do not consider the rest of the compounds, then also you can choose it. And see, in option B only C is at highest position. So that is why you can easily choose this answer. Even if you, because of lack of time, even if you can't consider the molecules, if you are sure about it, if you know the structure of mesitylene, you can answer this question. So after C, it will be A, because we have 2 methyl groups. Then it is E, because there is no electron withdrawing group. Because bromine is, it will also deactivate the ring by pulling electron density. And that is why after E, we have B. But NO2 is maximum, that is its capacity to decrease the nucleophilicity for benzene, it is a maximum. So that is, it will be at the last position. Okay. So option B is the correct option. Correct IUPAC name of the following compound. Here we have C double bond O COH, but we will start the numbering from here. It will have more priority. And even if you are confused about it, don't worry, because all the names, it is ending with enal. Now enal means what? Enal means in plus L. So there will be some CC double bond and there will be some CHO group, but that is common for all. So based on that, we don't have to choose any option. So if numbering starts from here, number 2, 3, 4, 5, 6, and it is ending at 7, because that is also another carbon. So at 6 position you have NO2 group, at 4 position you have CC double bond, and you also have a methyl group, and at 3 position you have keto group. Now methyl group, M will come before N, which is for nitro group, right? And after N there will be oxo N, alphabetical order. So methyl you should write first, after that nitro, and then oxo. So when keto is here, not the main functional group, so that is why we are using the term oxo. So 4 methyl 6 nitro, because the position of nitro is 6. Okay. 4 methyl 6 nitro, then we have 3 oxo, and the double bond position is 4. So this should be the correct option, isn't it? 3 oxo, then hept. Hept is for 7, though all are hept except the last one. And position of double bond starting from 4. This is the carbon where double bond is starting. So double bond position is 4. So 4 enal. So option C should be the correct option. Fine. Which of the following is most stable? So here also we have to consider aromaticity factor. So the first one, here if I simply write all the conditions for aromaticity, 4n plus 2 rule, then there should be, it should be cyclic, it should be full conjugation, and it should be planar. So all the condition must be fulfilled. Now most stable means what? The species which will show aromaticity, that will be most stable. Now the first compound, you will see all the conditions are fulfilled. If you consider 4n plus 2, n value 0, it will give you simply 2. And here you have 2 electron. Conjugation is possible. It is cyclic. It is planar. So it is aromatic. I am writing here A. Then the second compound, here we have negative charge, and that means total number of electron is 4 pi electron. So it is not matching 4n plus 2. It is basically matching with 4n, where n value is 1. So it is basically anti-aromatic, because other conditions are fulfilled: cyclic, full conjugation, planar. Come to option C. Here also it is matching with 4n, that means it is also anti-aromatic, total 4 electrons. And the last one, here conjugation is possible only in this part, like this. Positive charge will be here, negative charge will be here. But these two are basically sp3 carbon, so full conjugation is not possible, though it is cyclic. But this part is not planar, only the left hand side part is planar, but we have some sp3 carbon, so it is not planar, full conjugation not possible. So this is it will be basically non-aromatic, something not so stable like aromatic, not so unstable like anti-aromatic. But it is simply asking which is more stable. So option A will be the correct option because it is actually aromatic species, right? Which of the following carbocations most stable? Now we have to see in which case maximum amount of stability possible. If you consider the first one, this type of resonance is possible, right? Now this is basically, okay, let me draw it. It will be, now positive charge will be here, it is OCH3, and here we will have CC double bond. But remember, this double CC double bond, it can also take part in resonance with the OCH3 group. That means it cannot show the full conjugation with the positive charge. What about option B? This type of resonance is possible. That means now double bond is here, positive charge here, like this. Okay, but remember, the large double bond, it can also be engaged in resonance with the OCH3 group, so it cannot show the full conjugation with the positive charge. What about option C? In this case, this type of stability possible. That means now oxygen is positive. This is the after resonance the structure. So here also we are getting some stability. But in the last one, you will get maximum stability. See how extended is the conjugation. It is true that in C also we are getting some stability, but here we have more extended. You have only one CC double bond, here you have two CC double bond. So this type of extended conjugation, the higher is the extent of conjugation, that means more will be the stability. And that is possible only in the last compound, which is compound B. Okay, D. So this should be the correct option. The correct order of nucleophilicity. Here, nucleophilicity means negative charge if you have, and if you have a neutral species. So obviously, the neutral species cannot be more nucleophilic. The negative charge will be more nucleophilic, right? So you can compare lone pair and you can compare some fully developed negative charge. So this will be more nucleophilic. Now in the first case, we have F minus. So in both cases, we are having some negative charge. But remember, F is more electronegative than oxygen. So it cannot donate this negative charge very easily. So F cannot be more nucleophilic. So this is not correct order. Next we have lone pair over oxygen. But here you have directly negative charge over oxygen. That means HO minus should be more nucleophilic because we have already the negative charge. Same explanation you can also give here. ROH means this is alcohol. Here, if it is acting as nucleophile, it has to donate this lone pair, attack through this lone pair. But when it is RO minus, direct negative charge we have. So RO minus should be more nucleophilic. This is also not correct. Now last option we are left with negative charge over nitrogen and just compare with this lone pair over nitrogen. So this should be more nucleophilic. So this is the correct order of nucleophilicity. Okay, so we are at the end of the session. Thank you for listening.